Welcome to this presentation on our paper with my collaborators on the generation of gravitational waves from really decaying turbulence. So in this paper, we study a thermal first-order phase transition, which, as you may know, does the following. You have bubbles that nucleate in the medium, that expand, collide, and then eventually produce sound waves. In our paper, we study actually the long-term evolution of it, in which we expect shocks to develop and convert the acoustic phase into a turbulent phase. So the purpose of our paper is to model decaying turbulence semi-analytically, validate it with numerical simulations, and provide templates for LISA. Let me start with the basics. So we have a metric perturbation, which is sourced by the anisotropic stress of the fluid. And in radiation era, you can integrate it with a green function. This allows you to obtain the GV energy density power spectrum in the radiation era. And it depends directly on the UETC, the unequal time correlations of the anisotropic stress energy, P of pi. So in this paper, we do not model directly P of pi, but rather we express it in terms of the properties of the velocity field, which is better known in turbulence. So P of pi is a three-dimensional integral and depends on various quantities. It depends on the shape of the velocity field, so how it depends on the wave number. So in the inertial range, we expect a Kolmogorov slope, and in the infrared, we expect a causal slope. It also depends on the decay of the velocity field, so how it depends on time. Indeed, this is decaying turbulence, and we expect the velocity to decrease over time. And we have analytical arguments and also numerical simulations to prove that in the paper. It also depends on the decorrelation of the velocity field, so how it depends on two different times. So I will focus more on that on this presentation. And in the end, it depends also on the projection factors on the right-hand side. And these guys are quite important. They are here because we have a vortical velocity field and also transverse traceless metric perturbations. When you take all that into account, you have these projection factors that appear and that prevent you from simplifying this integral. And in the end, you are bound to have 2 dimensions of space and 2 dimensions of time to integrate over, which we do here numerically, hence why it's a pseudo-analytical model. To give you an idea of how we build these unequal time correlations for the velocity field, I'll review the Gaussian random sweeping approximation. The idea is that you have a lot of small vortices in turbulence, and they are advected without being deformed by a locally uniform velocity field, big V. With this simplification, the advection equation becomes linear, and you can integrate the velocity field. You can also express then the UETC of the velocity field, which looks more or less like a Gaussian in terms of the difference time, but not quite, because it depends also explicitly on a certain sweeping velocity, which is expressed here, which is dependent on absolute time. So we have a non-stationary process, and also it's very difficult to calculate it. It's basically the 2-time correlation of big V. Now, before modeling this velocity field, I'd like to review some properties of the 2-point correlators. So if you take any stochastic process phi and define its kernel k, this kernel k satisfies the Mercer's condition. So you can see it as the following. You take any function f, which is well behaved, and you build the stochastic variable x. The variance of x must be positive, and hence this integral, this 2-dimensional integral here, must be positive for any square I cross I and for any function f. And this is not satisfied, obviously, by all the 2-point functions. In practice, this is a problem because k is often defined directly. Indeed, this is what we are going to do. And thus, this implicitly determines the stochastic function phi. Hence, this Mercer condition has to be imposed from the beginning. So this is the approach we take in this paper. We first make sure that we impose Mercer's condition from the beginning, and this drives our construction of the velocity field UETC. So there are different classes of kernels, separable kernels, which allow you to factorize the Mercer condition, stationary kernels. The proof is a bit more involved, but basically there's a direct mapping between a kernel and the fact that the Fourier transform of G is positive. And this tells you that a top hat kernel is not actually a kernel because its Fourier transform is not always positive. Hence, you will have ill-defined physical processes. In our case, we cannot rely on these kernels because we have a non-stationary process, and we use for that a process convolution kernel. It's defined as the following, and we can check in 2 lines of calculation that it allows you to factorize in some way the Mercer condition into something that is obviously positive. So in our case, we take a specific choice of function g that allows us to have a kernel which is nearly Gaussian. It also tells us how the sweeping velocity depends on time, and it also gives us a non-trivial prefactor that we have to take into account to satisfy Mercer's condition. Then, now that we have this analytical model, we validate it using numerical simulations of a relativistic fluid in Minkowski space. So we have here the equations of motion. And we set in an initial velocity field as a Gaussian random vector field that we project to be purely vortical. We record regularly the velocity power spectra, the UETC, as well as the gravitational wave spectra. So you see here 2 snapshots of our simulations, the initial conditions on the left, which are not exactly turbulent, and on the right-hand side, we have the state of the simulations, which looks a bit more turbulent after a certain amount of time. So here we try to show the comparison between data and the model for the UETC of the velocity field. So with scaled quantities, so that on this plot, the model predicts a Gaussian black solid curve. So our model on the right has to be compared with earlier model by Nixa and his collaborators on the left. And you see that for each color here correspond to a specific wave number along time. So all these colored lines should overlap with the black line, and we see here that our model improves earlier model by a huge factor. Here is the most important plot of our paper. So the black line is, we take all these analytical building blocks and perform a 4-dimensional numerical integral, and we obtain this black omega GW. Colored lines are taken directly from the numerical simulations, 7 of them for velocities ranging from 0.3 to 0.03. The gray line is an analytical approximation, the formula of which I will show later, which, as we show here, gives a pretty good fit to omega GW. Now, one limitation of our work is that we don't take into account a growth phase. So far, we've assumed that turbulence sets in instantaneously, which is obviously wrong. And we've tried to model phenomenologically this growth phase in 2 different ways, either by a C0 growth phase, a linear growth phase, or a C1 growth phase. So this gives rise to this dotted and dashed line that you see here, and that tend to decrease the energy at large frequencies. Okay, so here is my take-home message. In this paper, we built a semi-analytical model for decaying vortical turbulence. We validated each building blocks as well as the omega GW in total with massively parallel numerical simulations. And we provide this nice formula, this analytical template that can be directly used for LISA to model decaying turbulence. In the future, we want to understand a bit more this initial growth phase that seems to be very important to give precise estimate to LISA, at least at high frequencies. Thank you for your attention.